introduce Josh Reich, who's visiting us from Princeton. He did his graduate work in New York, so I guess went across the river, different side of the world.
It's really weird over there.
I know. Columbia and Princeton are such a different animal. Josh is going to tell us about some really exciting work he's been doing on how to compose software-defined networks. So, some of our students have been looking at that as well, although you'll see pretty quickly from the talk that they've been coming at it in sort of a more formal programming language field, which is why we have a number of folks in the room as well. So with that, I will try to give Josh most of the hour.
Thanks so much for the introduction. Thank you guys for having me here. I appreciate the fantastic turnout. And I'm going to be telling you about our recent work, which is really focused on bringing modularity that we find in a variety of other areas of computer science to the discipline of programming software-defined networks. And this is research I did with colleagues mostly at Princeton, one at Cornell. So, this is just kind of a throwaway intro. Networks are complicated. And if you haven't seen this infographic before, it's kind of a neat mapping of a variety of standard network protocols along the layers of the OSI stack. Some of them aren't really applicable to what we're talking about, but the general takeaway here is, there's a lot of complexity. There are a lot of protocols and networks, and many of them overlap in functionality with one another. And of course, the infographic I showed you is just a subset of the complexity in the network. There are more protocols out there. There's also all sorts of vendor-specific stuff that's put into their hardware, whether it be extensions, APIs, or just plain old bugs, middle boxes, software switches, and so on. So software-defined networking, if you're not familiar with it, this is the 2 slides I'm going to tell you about it. It's basically an attempt to manage this complexity and make networks programmable. And it starts with the switch. And the switch is essentially, if you want to think about it in PL terms, a packet processor. It takes packets in, transforms them, and produces more packets out. And typically, this is implemented in hardware using a TCAM-based flow table that's hooked up to some software that's updating it and doing some kind of other logical management. But the flow table, which is really the core of the network switch, is going to essentially take packets in, look at the packet headers, match them to some entry in this flow table, and then do whatever actions are specified in that table entry, whether it be a drop, a forward out a certain port or set of ports, modifying some of the header fields before sending it out, et cetera. And software-defined networking basically takes this, says, OK, we have these packet processors, these switches in our network. We're going to introduce a controller platform that talks to those switches. And the controller platform gives us this nice network-wide visibility and control. And the communication between the controller platform, what allows the controller platform to modify these hardware flow tables on the switches, is some kind of direct control via an open interface. And OpenFlows become the de facto standard for doing this kind of thing. And of course, you have some kind of application that's actually running on this controller platform. So you guys, so many of the researchers that I spoke with already today have told me about fantastic work that's being done over here, really addressing kind of this southbound, how we control the switches efficiently, how we manage our controller in order to use whatever the abstraction we have for communicating with the switches well. And that's a very sort of important problem space. It's not the one that I'm going to be telling you about today, because there are actually 2 sort of SDN interfaces. We've got our hardware interface, OpenFlow, on the southbound side, as I'll call it, between the controller platform and the hardware. And we've also got an interface to the programmer. How do you actually write this controller application? And what should that interface be? And that's the question that our work is really focused on. So one simple option you can do is you can take your southbound interface, OpenFlow, and use it as your northbound interface, wrapping it in some standard programming language, so you have the ability to do loops in which you iteratively install new entries in reaction to events and so forth. And this is a very popular kind of natural first choice. A lot of very popular controller platforms are using it at the moment. And these controller platforms primarily have been focused on issues of sort of how do you make the southbound side work efficiently? How do you prove it's correct, say, with NetAll? How do you take your network in the Onyx work and present it in sort of this robust database kind of way? But this type of approach where you use a relatively low-level interface from the controller to the programmer has some shortcomings, particularly if you want to combine many networking tasks together. Say, even simple examples, you want to route and monitor, load balance, and firewall all at the same time. You tend to run into real problems when crafting these applications. Particularly, they end up being very tied together. And so you get out very monolithic programs, which are difficult to write, very hard to adapt to new uses, move to new network topologies, debug, et cetera. So all of the kind of standard problems of non-modularity. So specifically, what kind of problems might you encounter? Well, I'm going to show you right now two rules, which are in a sort of simplified OpenFlow syntax. So let's look at the rules on the left-hand side for you, the green box. We've got essentially something that has a match. So we've got on the first rule dest IP 10.0.0.2, another matching .3, and finally a wildcard at the bottom. Then you've got an arrow and a set of actions, in this case a single action, forward out a particular port. So essentially, traffic that's going to 10.0.0.2 is going to come out, is going to be forwarded out port 2. For 3, we're going to forward out 3. And once we've gone through the other cases, anything that's left over, which is all other traffic, we're going to forward out 1. So there's in actual OpenFlow, you've got explicit priorities that are being used. Here we're doing an encoding of priority implicitly to simplify the notation somewhat. And it's just going through the list in order. We've also got a monitoring program, which is the red box. And it's a very simple one. It says, if the source IP is 5678, then we want to count the number of packets coming from the source IP. And again, in actual OpenFlow, you wouldn't need to specify a count action per se. There's a counter that's kept there, but in this notation, it makes it very explicit and clear what's going on. So we, of course, need to combine these two rules and these two policies into a usable program. We could try sort of naive strategies for doing this, like, well, let's put our routing entries first and then our counting entries, but we end up getting a program out that forwards all the packets very nicely, but doesn't actually count any of the packets from the source IP. We could reverse things, and we'll count every packet that's coming from the source IP, but all the packets from the source IP won't get forwarded. So you can't naively kind of put these things together. There's actually this logical intertwining of the two policies when specified in this low-level way that when you turn them into a correct OpenFlow policy, you're going to end up having a cross product of the rules where you essentially have one entry for every entry in the first policy that includes the source IP, source IP match and the count action. And then for the non-source IP, we're going to repeat each of those entries once again. And this is old work from our group. You can take a look at the papers. They're kind of really neat. But this should give you a little bit of a feel for what the difficulties we might encounter when you want to take sort of your simplest routing program and your simplest monitoring program, and you can't even combine them in an intuitive way. So the goal that we have is we want to make software-defined network programming modular and move to a world like this, where you have one module for each task. They simply get composed together according to some recipe or specification that the programmer provides, and the controller program chugs around and installs everything on the switches. Yep?
How does this relate to the header space analysis work at Stanford? Is that not one way that you couldn't describe whether or not you had this overlap in the set of rules and say, look, we'll just compose these with AMs when you get the header space hit?
So the header space the ideas in the header space analysis paper, creating equivalence packets of equivalence classes of packets, and figuring out when you're going to get these rule overlaps and intersections can definitely be used to drive the design of a compiler. I think our group designed some of the compilation techniques, at least before that work came out. They don't, I think, focus on. I'm not sure if everything they've done could be adapted to what I'm about to tell you today, but it's possible. And we can talk more about that offline. So, sorry, just to, again, so we want this we've got several modules that we write independently, and we want them to be able to interact on the same traffic that's flowing through the system and produce correct behavior in a way that's intuitive and easy to write for the programmer, easy to specify, easy to reason about and test. And this is going significantly beyond, say, standard multi-tenancy kind of work. Stuff from the FlowVisor work, or Nicira's NVP system, or OpenStack's Quantum, where essentially in one fashion or another, you're subdividing your network into a set of slices where you have disjoint flows of traffic, either in terms of the bit match patterns that traffic matches, or in terms of the equipment or ports over which the packets flow. In which case, yeah, you can run a single controller on each of these slices independently, but each of those controllers is still its own mess of logic that's monolithic in nature. So, well, you don't need to see that. These pieces of work focus really on partitioning rule space and resources related to that. So that's really the main focus, although, as I mentioned, you can use them to get a little bit of modularity. So we need modules that can affect the same traffic and do more interesting, more powerful things. Where you've got, say, your load balancer, and it's going to partially specify how the traffic's handled, perhaps by rewriting the destination IP headers. Your routing module, which is going to partially specify some of the behavior, whatever the destination IP is after modification, it determines where the packet goes out of the network, where the packet goes out of the switch. So how do we actually combine these modules? How do we write them in order to get complete applications? Well, our Pyretic system is one potential answer to doing that. And so essentially, the abstractions that Pyretic offers are first a powerful policy language. So in Pyretic, if you wanted to do our previous application, you could write a route policy, which is simply equal to a couple of Boolean predicates that then have actions associated with them, a monitor, which is similarly designed, and you return the parallel composition of your routing and monitoring functionality. To go through that with a bit of animation, we've got our Boolean logic predicates. We've got our primitive actions that you can do, such as forwarding out a physical port, or in this case, forwarding out a counting bucket, which I'll tell you more about later. And finally, some type of composition operators, in this case, parallel composition. So each of these sub-policies in route is being done in parallel, and then we're going to be doing route and monitor in parallel. But there's more than just a powerful policy language. We also allow for a rich variety of different topology abstractions, which can be used for programmatic purposes. So for example, let's say you've got a legacy system. You've got some legacy Ethernet over here. You've got a legacy IP core over there. You had an old gateway that you want to replace. And you'd like to use a software-defined networking node, an OpenFlow-enabled switch. Because the traditional one's kind of expensive and doesn't give you the flexibility you want. So one option, of course, is you can take your new software-defined networking switch and write a really complex monolithic piece of code to do all of the things a gateway needs to do, which is act kind of like an end host for some purposes in order to respond to ARP packets on the Ethernet side, act like a rewriter in the middle for packets that are coming in on the legacy Ethernet ports that aren't destined out of the Ethernet. You need to act perhaps like a Mac learning component. Likewise, on the legacy IP core side, you're going to need to do some kind of appropriate compatible functionality. So there's a lot going on in our gateway. But there's potentially a different way to break it down, which is by recognizing that this can potentially be decomposed in a topological fashion. What do I mean? Well, if we were to take our single gateway switch and present it as a set of abstracted or virtualized switches, we could, say, make one switch, which is just going to act like a Mac learner, compatible with our legacy Ethernet equipment, and it's going to essentially inherit the 2 ports on the gateway that actually connect to that Ethernet island. Likewise, we can do something similar on the IP core side, and over here we'd want to run some type of SDN program, which perhaps has already been verified, so we know it's compatible with the legacy IP core. And then finally, we'll produce a third virtualized component, which is just going to do a much simplified and more constrained set of logical operations, which essentially boils down to doing MAC rewriting and forwarding packets coming in one port, out the other port. So our work actually provides 3 abstractions. I've told you about 2 of them.
Actually, can you rewind?
Sure.
Sorry,
No problem.
I don't understand where the topology came in over here. I don't know anything about that.
Sure. Okay.
But it seems to me like this is the same deal as what you had before, where you have 3 different, what do you call it, policies, and you're composing them, you're conjoining them, or taking their product. So I'm not sure where the topology quite entered the picture in this.
Okay. Okay. So in the previous example, what we were trying to do is we have 3 modules that we've specified independently from one another, or rather, 3 modules we want to specify independently from one another. And we need a way of specifying them and a language for saying, hey, I want to do these in some type of combination. Do one after the other and do the third in parallel. Okay. This situation is a bit different. We have one particular physical component which needs to do a complex set of tasks which don't easily break down into those kind of modules if you want to think about it as a single physical switch. So there's not a way of, say, taking this switch and say, OK, we're going to write module 1 to do Ethernet, module 2 to do IP, and module 3 to do the forwarding and rewriting logic that we can compose together in this kind of neat, crisp way, if we're viewing the single switch as a single switch. However, if we decide to view it as in a different topological abstraction, as actually being 3 switches in parallel, where one's inheriting some of the interface, another's inheriting some of the interface, and the third actually is connected only through completely virtual links, it allows us to break down our logic in such a way that modularization becomes very easy. Because now you can simply take your stock Mac learning component and run it on switch E. You don't have to make any change to it whatsoever. It sees this as a regular physical switch. It knows not the difference. So you run it. You know it's going to be correct. Likewise, on the IP side. And for the forwarding component, again, you write it as if it's a physical switch, and it's a nice, succinct piece of code that you can write. As long as the transformation that you've done and all the wiring that's included and the sort of stuff you need to do behind the scenes to make these 3 behave in a way that's, when implemented on a single switch, that's exactly like how they would have behaved if you actually had 3 physical switches, then you get this really nice breakdown, and you're able to reuse your code very easily and reason about it very easily. Does that?
It doesn't actually, but let's see.
Yeah. OK.
I mean, as I understand it, the main difference is that in the earlier case, the different policies had no dependencies on each other. They were quite independent. You just take that cross product and you go home. While here, the F can have dependencies on E and I. There's some observables maybe that are shared, or there's some information that's shared across.
Yeah. So.
But
OK, we'll take it offline. We'll take it offline also. Towards the end of the talk, if there's spare time, I'll show you a slide at the end of the deck that kind of describes a little bit more why this is a thorny thing to do without topology abstraction. But so moving on, our work offers 3 abstractions. I've told you about 2, policy and network. And the third is packets. And so if we want to think about this very abstractly, or using abstraction a little bit too much, we can think of each piece in our software-defined network as being something we can, take out of the physical world and consider in its logical formulation. So packets are something that are input and output. We're not necessarily going to be worrying about, oh, it's encoded, in such a bit order on the network, or so forth. We're thinking about it just as input and output to the system. Likewise, with the network, we're thinking about it as something that processes packets, and policies is something that determine the processing done by the network. And if you want an analogy, you can think of this as kind of analogous to a standard computing system in which you've got data that's going in and out of hardware, that's running some type of software telling the hardware how to process the data. So what are the specific abstractions we provide? Well, the packet abstraction, which I haven't told you yet about, is a powerful abstract model, and that's going to be the topic of the very next section. Network, we've got these network objects which can abstract the topology and potentially layer atop one another in order to facilitate module reuse and easy coding by programmers. And this policy language that allows us to take primitive policies that involve querying, predicates, and combine them in a variety of different ways. So today's talk is really going to be focused just on those three abstractions. And we're going to go through them one by one. So let's start with our packet abstraction. So an OpenFlow Packet, which is the standard kind of abstraction used in software-defined networking at the moment, gives you a fixed set of hardware matchable bit fields. So there's some fields at the beginning of the packet, and you can do bit matches against them in whatever manner is supported by that particular hardware. And you get a fixed set of these, and each of the entries, each of these fields has either 1 or 0 values. So if you're sending a packet, Ethernet packet that isn't an IP type packet, you won't be able to access, say, the source IP and dest IP field values. There are no values there. But source MAC and dest MAC are pretty much always available. And you can, of course, take a look at the spec or talk to me afterwards if you're really curious about that. The Pyretic packet model expands upon this significantly. It thinks about a packet as being a dictionary in which you've got, again, header fields, but now they're not simply names that have some kind of number of bits allocated to them, but they can actually be typed objects that you can check and test for correctness. Additionally, you don't have the fixed set of fields anymore. You can have virtual fields that correspond to things like the switch and the import, the physical location that the packet's at, or tags that you make up yourself, virtual switch, virtual import, user type, that can be very useful for inter-module communication and also for doing topology abstraction. And finally, you've got value stacks, which let you push additional values onto any given field that you want. And this turns out to be very useful, very convenient as a mechanism for implementing the kind of topology abstraction I illustrated previously. And we'll get to that in the third section of the talk. So kind of to sum up this abstraction, this is a not primarily programmer-facing abstraction from our point of view, or from this work's point of view. You could use it, but it's mostly here to support our other two main abstractions, the policy language and the topology abstraction. It gives you types instead of bits. It gives you a greater width in terms of what your packet looks like. You can just have more fields and greater depth. You can stack the values in any particular field. Again, it can be directly used by the programmer, and there's some interesting use cases for this, but we're mostly going to be focusing on it as a supporting mechanism for the rest of the talk. So I'm going to move, yep.
So what are you going to hang off the typing aspect of it, in the sense that I presume there's no runtime communication that looks at this packet and verifies that the bits are actually typed appropriately? Does that open up sort of holes in whatever property you prove
So the type checking is much more useful for the virtual fields when you're actually encoding some type of virtual object which is going to potentially go across the wire. And so then there's an automated encoding mechanism that maps this back and forth to some spare headers in the bits. And when it comes out the other end, then you can potentially do a correctness check. At the moment, we're not thinking about using the typing for anything else. Although there might be some interesting kind of things you could do if you wanted to implement this in like a net FPGA or whatever, and automatically analyze the bits. But I'm just kind of like shooting it out there. So in terms of the policy language, I've given you a brief taste of it in the intro. I'm now going to really kind of give you a deep dive, so hopefully by the time you're finished with the talk, you're both very clear on how this language works and might even feel comfortable trying to write a program or two, and also hopefully not too bored. So there are three portions of the policy language that I'm going to be talking to you about today. The first is a static policy language. So it's basically, it lets us write a set of statements or expressions that are going to be compiled down and can be turned into some rules that are going to be running on the OpenFlow switches in a sort of one-pass process. Possibly with some later intervention by the controller, but from the point of view of the programmer, nothing changes once you've established the policy. I'm then going to talk to you about dynamic policies, how we can take a time series of these static policies and create a policy which essentially acts like whatever the static policy that's most up-to-date inside it is. And finally, how you can actually use policies recursively and create recursive policies and what that might be useful for. So I've been a little bit vague about what I mean by policy, and so now I'm going to get very specific. A policy is a function that takes an input packet from some location and outputs a multi-set of packets at some set of locations, potentially different. So for example, I might have a policy forward to, which when applied to a packet P, simply produces the output set where I take P and produce a new packet by pushing the output equals 2 onto it. So this is basically saying copy P and add a field output equals 2. So the entire static Backus-Naur form is up in front of you, and I don't want to overwhelm you with the details, so we're going to go through each of these one by one. The first piece are these actions. You've already seen forward. I'm going to now show you our drop, which is very simple. You take a packet in, and you return an empty set, nothing there. We've also got an identity function, which will prove very useful later on, actually, that takes a packet and produces a singleton set with the same packet. We have packet header modifying operations like pushing a new header, pushing a new value onto a specific header, or popping a value off a particular header, the topmost value. We're also able to move values from one header field to another. So when I say move from H1 to H2, it basically is going to produce a copy of P in which whatever value had been at H2 is now at H1. Finally, forward, which you've seen before, we can actually write as a derived policy as being a push. And flood is actually a union of forward policies for where every output port is an output port in a minimum spanning tree on the network. Sure.
Is push strictly an extension, or is it an override? It's not really.
OK, so push is using the Pyretic packet model. So when I push a packet on, I'm actually adding a layer to the stack on that header field. So if I say push a new switch name, then I've got two switch names, the topmost and the previous one.
There's no way in one step here to say change something.
So move does let you change something, but it's not the one step. So what you're looking for is what we call mod or modify. And the way you get that with these primitives is you'd sequentially compose a push and a pop on the same header field.
Why didn't you do that given that you, oh, I guess I understand. Given that you have move, why is move a special case but modify isn't?
So move is a special case because we don't have a way of storing popped values.
Okay.
Yeah, so there are a variety of different ways you could, reconfigure that or refactor that. This is just the one we chose.
So I'm trying to get ahead of you, and maybe we'll talk about this, but you have an explicit drop, which is sort of different than typically you just fall off the end. And so I can imagine you could do this because then you might analyze that every case was handled, but then you've got the halting problem issue. So what value do you get out of explicitly dropping as opposed to what we traditionally do, which is, I don't tell you what to do, drop it.
The truth of the matter is it's really more of a notational convenience than anything else, as you're going to see in the very next slide when I talk about predicates. But I guess here's a concrete example of what you can do with a push. Actually, that really should be a move. But anyway, so predicates, essentially what do they do? Well, we can have a predicate, say all packets, that acting on any internal policy, X, and applied to any packet P, just says, OK, apply X, the policy inside, to PR packet. Great. No packets. X, P, we end up just dropping. So we get rid of it. So over here, you can actually think of drop as really being derived by putting the predicate no packets on any particular policy, you don't care which one. And you could make this output the empty set instead of having drop output it. It's kind of syntactically convenient. But in terms of analysis, which you had mentioned before, I don't think it's necessary to do any of the kind of proofs that one might want to do. It does make it easier to read. Sure. Okay, so the X is a policy. And policies right now, so far as we know, are just these set of actions. There will be other policies later on which can be worked upon in exactly the same way and have exactly the same semantics when predicates are applied to them. So all packets, no packets, not terribly interesting. So we also have a match. You specify a header, field, and a value that you want to match. And basically what that comes out to is if, in fact, the packet's header, the value stored at that header field matches the value you're testing, then you're doing the action or the policy on packet P. Otherwise, you're doing drop on the packet. Likewise, we can actually specify topologically aware predicates like ingress, which essentially says if the packet is at an import that's one of the ports on the network boundary, then again, we're going to do the action that ingress is being applied to on the packet. Otherwise, we're going to drop the packet. Likewise for egress, but here it's the output that we're matching against. And of course, we can do Boolean combinators. So over here, we can take the intersection or the logical AND of two policies, P1 and P2. And what we'll find is the behavior that we get out is going to be equal to the intersection of doing P1 and doing P2. Similarly, if we want to do an OR case on these two, we're going to get out the union of what's produced by those two policies. And these are simple set intersections and set unions, which is important to note for later. And finally, we've got a negation operator, which has the expected semantics. And so one policy one might decide to write in a line would be, hey, if the packet's at an ingress and it matches a particular source IP prefix, then we're going to forward it out a given port, possibly because we want to monitor it, or process it further or provide some type of service that is going along that port. Next set of, so we've, just to recap, we've got our actions, which are very basic policies. We've got our predicates, which allow us to modify policies and create new ones. And now we've got our queries, which let us treat monitoring the network and asking questions of the network as if it's a standard forwarding operation. And so there are two particular policies in here that we support at the moment. One is packets, and the other is counts. Essentially, when you write a packets policy, you're saying, I want to see all the packets matching whatever the optional set of header fields are. So if we say source IP, dest IP, then I want to see all packets grouped by source IP and dest IP, and potentially a limited number of them. If I don't put the limit in, or I put a limit of none, then it'll just keep counting them forever. And the way this works is it just involves forwarding, a forward action, but not to an actual physical location, but instead to an abstract location that corresponds to a data structure that's going to keep track of, say, every packet in this case, and call back those methods that have been registered to handle events from that data structure. On counts, we're keeping track of counts as opposed to the actual packets themselves, and we can have a repeating interval. So say we're going to do this every 30 seconds or every 5 seconds. Again, we have the ability to group by header fields, and it's the same kind of deal, except we're forwarding to a counting bucket, and the particular bucket or counting bucket that's going to be created will depend on the input parameters.
Are these virtual destinations, do they receive copies of the packet, or does the actual packet sort of get queued and delayed until processed? Or?
So both of those are potentially viable implementation mechanisms for doing this. We're focusing kind of the abstract semantics right now.
So semantically, do I need to define a continuation for what to do after you get out of that bucket, or does the bucket have to have logic to figure out where to go?
So once the packet enters the bucket, the policy's done, the processing's done. The bucket itself may update a certain data structure, which may, take some callbacks that are registered, or notify some callback functions that are registered with some new piece of data, whether it's an aggregate, like a count, or a copy of the packet that was received.
So maybe I just, not understanding how you apply this, but I'm thinking, going back to your the very first example, you wanted to count something and forward it. So clearly I'm going to use this packets thing to count, or the counts thing to count it, but how do I also simultaneously forward it?
So if you want to forward it on the actual network and forward it to one bucket or many, what you do is you parallel compose those two policies. Just like you could parallel compose a forward out port 2 and a forward out port 3 to forward the packet out both ports. So it's just a straightforward application of that operator.
I copy it.
Yeah, you can totally think of it that way. So yeah, here's one example for exactly how you might set up a very simple one. So we're going to count every 30 seconds the source IP based on grouping source IP, dest IP, and switch. And every time we're going to register this function print using a when method that belongs to this particular policy. And that essentially says, hey, policy, this thing that I'm putting into you is one of the things you should call back anytime it's time for you to call back. And since this is a counting bucket, it's only going to issue callbacks every 30 seconds with a count, and print is going to print that count out. On the other hand, if this were a packet bucket, then every time a new packet was received, all of the policies that have been registered with when would get called, and you'd get a printout of each packet that's been seen by the network. And so finally, we have sort of what I'm calling derived policies, because they're really built up of the previous three pieces of the previous three syntactical sets that I've shown you, the actions, the predicates, and the queries. Some of them are pretty straightforward. oh, okay, we're going to do an action on a packet, we're going to do some querying, or we're going to apply a predicate to one of our other policies. We've also got some really neat combinators. The first one, and this isn't terribly novel because it's been done in our previous work, is this parallel composition operator that we just discussed as the way you can forward out multiple locations at the same time. And semantics are pretty simple. It's basically take the union of the two policies applied to the same packet P. What is very novel and actually quite powerful in this work is a sequential composition operator that basically takes one policy and another, and when applied to a packet, does the following. For every packet produced by applying the first policy to the incoming packet, we are now going to apply the second policy to that output of policy 1 and take the multi-set union. So this is a multi-set union as opposed to a single set union before. And so what this basically lets you do is write one policy, write another policy, have the first policy go first, and the second policy work on the take the input provided by the first policy as output. And I'll show you a concrete example of that momentarily. But beforehand, we also have a convenience function, a convenience policy. If some predicate, then do C1, otherwise do C2, and it has semantics, which can be clearly defined by using constructs already explained. So we can write something kind of interesting like this. If we're matching on a particular destination IP, then we can say modify the destination IP by doing a pop and a push. So this is kind of a pseudo rename operation in a load balancer. If it's not matching that destination IP, we're just going to apply the identity function so we don't drop it. And then everything coming out of here, we're going to forward out a port 2 in this case. So now this lets us start writing more interesting kind of programs, more powerful ones. So we've got a load balancer for a IP destination 1, 2, 3, 4. And essentially what we want to ensure is traffic from clients in IP prefixes starting whose binary representation starts with 0 are going to go to 10.0.0.2. Those rest are going to go to .3 server in our network. So what do we need to do? We need to be able to rewrite these headers. And this load balance, in fact, does exactly that. First concatenated sub-policy is we match on the source IP, the destination IP, and we do a modification action. No forwarding being done. Likewise on our second action. And finally on our third action, there's no set of priorities, no ordering in which these policies apply. They're simply all being applied in parallel at the same time. But we've calculated a disjoint set by saying, OK, those packets which don't match that destination IP, we're just going to pass through unmodified. And now we can take our load balancer and the router and monitor examples I showed you before, now in a slightly expanded version of the syntax. And putting them together is as simple as writing return a new policy, which is apply the load balance policy sequentially composed with the routing policy, and do that all in parallel with our monitoring operation. And our system will chug away and produce all the low-level implementation stuff you need to actually realize that. And as a programmer, it's super clean and hopefully something that will appeal to you. So I've told you about static policies. Now I'm going to take 2 minutes or slightly more to tell you about dynamic policies, because being able to combine modular behavior is very nice with these operators. But if the policies never change, what you can actually do tends to be significantly less interesting. So I'm just going to do this one by example instead of trying to provide a full semantics for it. by taking a look at how we might write a Mac learning switch in Pyretic. Okay, so we're defining a learning switch. And one of the things our learning switch is going to do is it's going to declare a query saying, hey, the first time I see a pack with a unique source MAC and switch combination, I'm going to keep a record of that packet. And what am I going to do when I get those packets? Well, I'm going to do some kind of update. Finally, what's the internal policy my dynamic policy is going to have? It's going to be flooding all packets at first, and at the same time sending all of the queried packets, forwarding all of them as per the query policy. So what does this update do? Okay, well, the update's going to take a packet, and it's actually now going to modify what the self policy is, the internal self policy is. And the way it's going to do this is by saying, hey, if I'm matching a destination MAC, that's the packet source MAC, if the new input packet, and the switch is the same switch that's in the packet, then I'm going to forward the packet out the import because I know that's the case. Because now I know if a packet came in from a particular import for from a particular source MAC, I know that sending new packets to that MAC address when they're the destination from the switch, it's clearly out the port they came in since that's the closest port to them. That's kind of how Mac learning works in a nutshell. So I'm going to now update my policy. So if I've got something new to learn, then I'm going to set myself to the newly learned policy. Otherwise, I'm just going to keep things as they are using my if statement. And finally, I want to run this thing. Well, all I do is I get my set up a main program and return my learning function wrapped in this dynamic call, which turns it into a fully fledged dynamic policy. And there's just a little plumbing to do that in the code. I'm happy to talk about that offline if you're really interested in the details. They're also in the paper, I believe. So finally, recursion. Well, once we've got these dynamic policies, it enables us to very easily write policies that recurse. For example, I can write this extremely stupid and useless policy, which will essentially kill your interpreter, where I have an infinite policy that just keeps setting its internal policy variable equal to itself ad infinitum. So what would something like this be good for? Well, this particular example is good for nothing ever. But there is a case where, at least one case where recursion is extremely valuable, and that turns out to be certain variants of network abstraction, which I will now tell you about in the final portion of this talk, where we talk about the network abstraction that Pyretic offers. So the simplest abstraction that I can demonstrate to you is a many-to-one abstraction. So we've got, say, two switches somewhere in the network. They're connected to one another, and each of them has at least one output. And what we'd like to do is we'd like to aggregate their capacity, aggregate their functionality, either to make things easier for the programmer or potentially to get more resources. So we present a virtual switch which has a much bigger flow table or more input-output capacity of the controller than the actual underlying switches have either independently. And we're going to derive that new network. So we're going to take switch S2, switch S1, switch S2, and we're going to make a new virtual switch where the port on virtual switch 1 maps to the port 1 on S1, and the port 2 on virtual switch V maps to port 1 on switch S2. So in order to make this work programmatically, we need to be able to provide three things, or three sub-policies. The first is an ingress policy. And this ingress policy is essentially, and over here it might be worth just going back and taking a look at V. When we've got a packet that goes into V, it's actually going to be coming in on the physical network. So we need some way of taking that packet and lifting it up So it's now essentially in the virtual network, in the abstract network where V is, and we can run some kind of client policy on V. Likewise, once the packet's entered V, it actually needs to be routed. It needs some kind of fabric policy. That might be as simple as just sending it out the same port it came in which case no additional engineering needed. But if we're going to send it out port 2, well, we need to now forward the packet across this link, get it into S2, and have S2 match it appropriately, and recognize it needs to go out port 1. And of course, that last step going out involves a devirtualization. We need to recognize that we're egressing the network and make 1 or 2 modifications. So ingress policy tags and lifts our packet from the physical network into the derived network, the underlying network into the derived network. The fabric policy is going to be what moves packets through the virtual switch or series of virtual switches. Yeah?
Question actually.
Sure.
The previous slide. So you're taking two
This one?
networks, yeah,
Two physical switches.
switches,
Sure.
and putting them into some sort of derived network. Previously, we talked about learning, right? And so we can learn. How do you keep state synchronized, get it in line card speed with the derived network?
Oh yeah, how do you keep states synchronized in line card speed when you're doing this kind of?
Or are you blocking when you need to keep state updates?
So there's a bunch of interesting work, some in our previous work, some that's been done by other folks, addressing some of those issues. That said, not all of the features that I'm presenting to you today have we yet implemented at like line speed, all in the switching tables. We have pretty good ideas about how to do all of them, and I've got some extra slides if you want to talk more after I finish up this section. We can get into that a bit deeper, but that's sort of the basic answer. So our fabric policy is going to move the packets through the virtual network components. And finally, our egress is going to untag our packets and send them out into the physical network. And all of these policies that are specified by the programmer are used by a virtualization function that is provided in the core portion of our code base. And essentially, the way this thing works is it says, OK, I'm going to take the ingress policy that's been specified, and I'm going to apply it to the incoming packets. Then I'm going to apply whatever the policy, the guest policy, written against the virtual network is. Then I'm going to lower that packet down and hand it off to the fabric policy, which is going to move the packet through the virtual network, or simulate moving the packet through the virtual network. And finally, if applicable, I'm going to apply the egress policy and release the packet from my domain. So for example, in the previous case, we can write this in one line, return virtualizing, say, a Mac learner by using a pre-created and infinitely reusable big switch virtualization object, which includes inside the object the ingress, the egress, and the fabric policies, along with a couple of other convenient pieces of functionality to enable that. And so if you want to see actual tangible examples of these policies, I think I'm not going to talk through them right now. OK, so is anyone interested in seeing the details of this example? Or is there great interest in the room? OK, I'm going to take that as a no. We're going to move on to something slightly more interesting, which is how we actually apply this to a one-to-many translation, our gateway. And this will have a nice animation. So we have this gateway abstraction. And here things kind of get challenging and interesting, because essentially what we need to do, interpretively for correctness, and at some point make sure we have an equivalent compiled policy in order to make this efficient, we need to make one physical switch really appear and function logically exactly as if it were these three virtual switches connected according to the specified topology. And so the way we're going to do that is we're going to leverage our packet abstraction from beforehand. And we're going to start by having a packet that's traveling in the physical network arrive at port 2 on our gateway node. Okay, when it arrives, we've got a whole variety of different fields. I'm just showing you the applicable ones here. Switch is G, the import's 2. It's got a particular source MAC and dest MAC. More interesting are its source IP and its dest IP. So it's a packet from inside the Ethernet network that's going somewhere else to the outside world. So the first thing that we're going to do with our virtualized function is we're going to apply our ingress policy. And in applying our ingress policy, we're going to immediately tag our arrived packet as being at the corresponding virtual port. So vSwitch E, vimport 2. And then we're going to lift the packet up into our virtual network. And how do we lift it up? Well, we get to use our neat stackable field values. So we're pushing E and 2 on. So now if we have a client policy that's going to operate on this Pyretic packet, it's going to operate only on the topmost layer of values. So as far as the client policy is concerned, this packet is exactly at the physical location in the network, E2. And we can run that policy, in this case MacLearning, which is going to determine a physical output on the what it thinks is physical switch E that the packet should leave. Once we've run our client policy, we're going to lower our packet back down by pushing the physical headers that we had back to virtual ones and apply our fabric policy, which is going to determine where we go next. And in this case, well, if we were at E3 as our output, then the next place that our packet's going to move is going to be F1. So in fact, we're at vSwitch F and vimport 1 now. Now what's interesting here is we're actually going to take advantage of the ability to write these recursive policies, because we essentially need to run one switch and then another switch and then yet another switch 3 times in one evaluation cycle. And so we recurse, which applies the ingress policy from scratch. In this case, tagging us as being at virtual switch F and virtual import 1. We're going to lift our packet up, which is going to pop some values and push them elsewhere. So now it appears like that's the physical location of our packet is at F1. Going to apply our client policy, which is going to do some non-interesting MAC header rewriting and also determine the new forwarding port, which is F2. We're then going to lower the packet, apply our fabric policy once again. And of course, we've written a recursive fabric policy. So we're going to again apply ingress one more time, lift our packet up one more time, apply whatever the routing policy is that our legacy IP core component does. Finally, lower our packet down. And we've established that we're doing voutport 4, which is now when we apply the fabric policy going to tell us the actual physical output should also be 4. And the egress policy now gets rid of all of our virtualized headers and sends our packet along the way. So this provides, yep. Where do you decrement the TTL? So, okay, so 2 things. So in terms of the TTL, conceptually, at each step along the line, you would want to do the decrement operation. Ideally, what you would have is some hardware that would allow you to do multiple decrements to the TTL. I think OpenFlow Spec 1.3 does that. I'm not sure that the OpenFlow Spec 1.0 does. In those kind of cases, you can, of course, send it back to the controller, but that's not going to be efficient. So it's kind of a really lame answer. Probably we would need to come up with some kind of workaround or trick for, yeah.
Like,
sure.
I mean, the reason you need a TTL is in case you have some kind of problem in your network and you have this loop.
Sure.
But if you could give this program, you could maybe statically check it.
Yeah, so that's actually one of the interesting things. I mean, if you're dealing with one of these one-to-many transformations, you can think of a variety of different correctness properties for both checking the forwarding and also actually checking the compilation process. Because in order to compile this down, you're going to have to be able to unroll this several times. So you can do things like look at the diameter of the network or the length of the longest path within the network, and then use that as a basis for your halting criterion in doing that kind of loop detection analysis or so forth.
So it's entirely our blame, but we are unfortunately over the hour. So.
Okay, well, you know, we're at the summary slide, so yay. The summary is basically, hey, software-defined networking needs some kind of more modular, higher level facilities for programmers. I think the Pyretic system is a neat attempt to move in that direction. I think there's definitely a lot of unanswered questions and interesting work, and I have a whole variety of thoughts on getting efficient southbound implementations and some extra slides, so anyone who wants to talk afterwards, I'll be around and modulo my schedule. And yeah, thank you very much for your attention and for coming. And do we have time for additional questions?
Yeah,
or?
you can ask questions. I know some folks have to run off.
So at the beginning of the talk, and here on the summary slide, you mentioned that basically you're trying to target this programming, a way to program SDN networks, right? That's different
Yeah.
than the kind of southbound OpenFlow.
Yeah.
But in the meat of the talk, what you really presented is a way of specifying policies. So
Yeah.
do you think that policies are the right way to program the network?
So my honest opinion
Or
is
is this like an intermediate step towards something else?
so I think that when it comes to programming the network, we're still relatively like near in the progression of how this is all going to play out. You know, there are a lot of really basic abstractions, and the killer applications are, to me, unclear. I think there are a variety of potential killer apps, but you know, Nicira, most successful kind of software-defined networking company go out, they actually don't really use any of the software-defined networking technology, aside from they used to use the OpenFlow API to interact with their soft switches. And they could have used any other API. And in fact, now I think they've pretty much entirely abandoned OpenFlow as that interface. So I think figuring out what the things we really want to do in the network are and what the best way to write them is kind of an open question. And I think upping the level of discourse so we can talk about things using these functions and writing somewhat higher order things while still having pretty good access to the lower level functionality gives us a nice mechanism for exploring that space and figuring out what the correct answer is.
I had a question. So, what does Pyretic compile onto? Does it compile onto your previous netcore?
Yeah. So right now you can download our Pyretic VM. It's reasonably functional and very cool. It has all these examples in full code that you can run and test yourself, integrated with Mininet, but it's just an interpreter. So this work, the published work, is really just focused on that question. So the goal, right now we're actually having a big group discussion. We're deciding whether we're going to write a serious, and by serious I mean non-microflow-based compiler, because a microflow-based compiler is basically like doing an interpreter but caching results on the hardware. We're either going to write one from scratch for Pyretic, or we're going to leverage our old code base and compile to it in some standardized interface spec, like encoding netcore policies, what we call them in previous work, as JSON objects. So yeah.
Get the soundness properties of netcore.
Yeah. Well, theoretically we could get the soundness properties by redoing this, but actually one of the potential implementation platforms is this new OCaml verified compiler. So some of the code's in OCaml, but a lot of it's actually in the COC proof system. So you can write your COC proof that'll generate the OCaml code that will do the actual compilation, and so some of it's actually verified correct. So I think we actually are probably going to do that. I think that's the most likely option.